Hello, everyone. Welcome back to the next session on the advanced topics on DAOS. So hopefully during the hands-on session, we tried out some basic simple tests uh, on how to create containers, how to do I/O with POSIX interface, and how to see a quick difference between Lustre and DAOS, and see some performance gains over there. So in this session, we will go a little deeper, advanced topics on how you can even make the better use of DAOS. So, but most of the topics here are on the concepts of how DAOS works and how it can be extended and how it is benefiting the exascale high performance storage. Most of these things, it is just good to understand the concepts of how it is delivering this 25 to 30 terabytes per second. And it might help with some of the tuning knobs in experiment wise or in job script wise. There are very few changes. Maybe you'll just change one or two configuration parameters, but the working is very simple. So this concept will help you to understand those configurations. So to get started, we saw what is a pool. Pool is a dedicated storage for your space. And containers are more like your directories where you drop all your data sets. And inside a container, everything is an object. So that's where the OS comes from, distributed asynchronous object store. But you will not be interacting at the object level. You'll just drop files, images, dataset, checkpoints, but that will be stored as an object. So an object is more like it can be defined anything as a simple array of numbers or a distribution key value pairs, like a distribution key and an attribute key, and so on. It is also important to know that you should not create one file per container. You should have very few containers. Yeah, so after you create a container and mount it, you would feel like it's another Lustre space where you cd to that directory ls and do all your files and IO. But underneath all this POSIX level interface, it's a DAOS container with a lot of objects, and it is distributed across different storage spaces. It just presents you that conceptual view of a file storage kind of an hierarchy to you. But we'll be interacting at this space just to know what's happening underneath. So you don't have to create or destroy objects or set some ACLs or any particular way to place your objects. All these are taken care underneath. So all this provides you with a very short time to the first byte. So an object can be an array or a key value store. You can theoretically have like 1 trillion objects in a container. You can make use of this object container and create any type of container you want. You want a POSIX file hierarchical container or a KV key value container or Python container, graph containers. You can bend DAOS to make it present you any type of representation that you want. So how do you see all those things? Like, how do you see your objects? You just drop files there. But if you really want to see where are my objects, so there are like 1024 DAOS nodes. Each has 32 targets with persistent memory and SSDs. So if you really want to see where exactly your file is chunked and distributed and placed, you can run some of these tools to see where exactly this is getting placed. So the DAOS FS scan pool name and container name would show you certain information about your container, how many objects you have, files, and so on. and you can point the path in your pool and container and get a particular object ID, and then you can use the DAOS object query on that object ID to get where exactly, which are all the nodes where the object is being placed. So you can see it's out of 256 DAOS servers, it's using the 56th DAOS server and the 5th persistent memory and so on. This is just to understand how your files are being placed at different locations. So what does all this offer? So how does this play with the concept of object stores? So previously, if you have in the Lustre world, if you have a large data set, like petabytes of data coming from some astronomical, maybe from satellites or some antenna, or and you have this multi-dimensional array with maybe the weather data from 1930s, and for each days you have like pressure and different variables. So you might have to load the entire data onto the memory, get the exact value, and unload it and get the next set of you might have to do all this load and store, which are costly and expensive. But with this object store, now you can exactly slice which dimension you want or which particular object you want. You don't have to load the entire file or data set. All this, and it also builds a structure on the fly. So you don't have to load this entire data. So that supports different creation of data, querying, analysis, and different IO patterns, which were previously hard. And it also helps to build a structure for any complicated data sets that you have. So yeah, so the DAOS ecosystem, currently the DAOS cluster on Aurora has persistent memory and SSDs. Maybe in other locations, even if they don't have a persistent memory, we can still use DAOS with SSD and DRAM. So it's efficient for unstructured data, for accessing small data. It delivers high bandwidth, low latency. There is no locking, no client tracking, or any centralized data servers, or no global object table. So next, I'll move on to certain concepts on how you can configure certain storage efficient variables. So basically, there are these three things like erasure coding, replication, and fault tolerance, fault domain. So all this is just to make efficient storage of your objects and data sets, and provide you with a greater fault tolerance against multiple failures. If you have like very tiny metadata intensive data, and you want it to read fastly, then you can use the method of replication, where it duplicates the entire data sets in different places, so the reads at scale are efficient. Whereas erasure coding uh, helps you to split data into different fragments with the parity bit and the data bit. And I think it uses the Reed-Solomon algorithm to place data efficiently, especially for the large data, and rebuild them. So what happens is it has to run this algorithm at the back end to rebuild. So that might add some lag to the latency to the bandwidth. So erasure coding is better for large, replication is better for small workloads. Uh, and so here I'm showing a simple conceptual representation where a client writing data to the engine, the backend storage, but it doesn't have any replication or erasure coding. So basically, if this node goes down, your data is lost. But you will have a really high performance in accessing this data from the storage. So whereas so this provides high performance but low data protection. You can also use replications to have multiple copies or use the erasure coding. These are all different ways how DAOS handles the data at the back end and how you can configure them. I'll also show how to change and set all this configurations. So the last concept here on the topic of efficient placement is redundancy. So by default, redundancy uses fault domains. So here, the fault domain can be an SSD or an engine or a server on an entire rack. But on Aurora, we have this two engines as the fault domain. So even if two engines goes down, they will be able to build back the data. And you can change all these variables by setting the properties. So all this concept that I explained till now can be condensed to this just one variable. You can set the properties, change it to artifact 2 or 3 or 1 or 0, and you'll be able to see the performance difference during the container DAOS container create. Yeah, so the fault domain is you set the redundancy factor to 2 or 3, and you won't even see if a server goes down. So there'll be an automatic online self-healing, rebuilding, and build back the data. Everything is happening on the background. Sometimes you might see rebuild busy on your DAOS pool query, or even the state is equal to degraded. So you don't have to worry about all these things. This just shows that it's rebuilding your data and all your data is safe here. So basically, we saw three different things: redundancy, no redundancy, and within redundancy, you have this concept of replication and erasure coding. And this is how you provide the configuration. So if you want 2 levels of redundancy, you set the properties equal to RF2, and you can set the object class as EC16P2 or replication 3 for different directory level object properties or file properties. Or even if you want to make it more efficient, you can use this configurations. So all this will go into these configuration variables in the container DAOS container create. Previously, we were using just the first 2 lines here. Now you can append all those variables that we saw till now into this command. And you can also verify, never trust on the defaults. You can just do a container query and see what kind of redundancy factor it has, what object class it has, and so on. So this is on the replication, erasure coding, and redundancy. So this is a simple test. So we just changed this couple of values here on the file object class and the properties. We just turn these 2 knobs to see how the I/O performs for the hack applications. So the red line here is the no redundancy. So it's just RD0. You can see it gives the best performance for when you increase the amount of I/O. But the problem is there's no data protection. So you will lose the data if a node goes down. Whereas as you change different configurations, you can see where you get your best configurations with data protection. So this is where all this would help, everything we saw till now. So this is from Hack, and you can also do some really fancy configurations. You can have a container with one file having a different object class, and another file can have a completely different object class, and so on. All this is possible within the DAOS container. So Next, we'll be moving on to the different interfaces that we saw before. Till now, we have seen what is an object, what is an object store, how DAOS stores the object in the backend, and what is replication, redundancy, and fault tolerance. In the morning session, we tried out POSIX interface. Basically, we just mounted a container and then use that path to store your dataset files or checkpoint files and read from there. And before that, we had a session on MPIO and IO libraries. So DAOS supports all those libraries and even make it efficient. So if you want to club both the MPIO interface with DAOS, you just create a file, a text file or something, and provide all this configuration. So so MPIO, you have all this tiny data sets that you want to write from all the 8,000 compute nodes. You can select some aggregator nodes and then club some of the small data set and push a big IO. You can provide all the usual MPIO configurations in a file, set it to the Romeo hints environment variable, and then you can just use as always. So moving from the POSIX MPIO world, there's not much difference on DAOS. Yeah, so most of these things we have seen in the morning session. So aggregation of small IO, collective IO optimizations, provide different IO access patterns, derived MPI data types. It's a building block for other parallel IO libraries like HDFI, NetCDF, and so on. So the last interface here is the most lower level, close to the hardware performance interface, which we call as libDFS. You can consider it like DAOS file system. And it provides a lot of APIs to directly interact with DAOS. This is actually not needed. You should be getting close to the lower level performance even with POSIX, but if you still want to develop DFS level APIs and make really, you really want to make some changes in your code, you can use DFS init, connect, open, DFS write, DFS read, and DFS disconnect. So it's very similar to the MPI one. And this one is with PyDAOS, PyTorch. So from the AI and LLM workloads. So one of the best thing that this offers is the framework, the distributed frameworks, and especially the num workers and prefetching that we saw yesterday. DAOS provides an easy interface to interact from the PyTorch level all the way to DAOS, and you can still make use of a higher number of workers to make your IO faster for dataset, data loader, and checkpoint. And this interface still uses the DFS level API, so this would be faster. Or you can still use the POSIX interface if you don't want to deal with it. Just provide the path to the temp full name, container name. Yes, seen most of the things that we discussed here. That's all from the interfaces. We have seen the POSIX level interface, MPIO interfaces, DFS level interfaces, and how do you interact with DAOS from PyTorch and PyDAOS and so on. So the next concept we'll be moving on to is monitoring DAOS. So let's say all this is great, but I really have a doubt whether it's actually talking to DAOS. How can I see? Because there are very less changes that I use on the code to use DAOS. You can use some of those monitoring tools that we'll discuss now. There are many ways to profile DAOS to see what's happening underneath. So the easiest one is to use the DIL interception library report. You just set this environment variables and keep doing the same MPA exec to the DAOS path, and you will see how the IO is getting broken down into different DAOS level calls here. This is just a quick test that you can do, very minimum change. And if you want some really intensive logging, you can use the DAOS client-side logging. Client for DAOS is the compute node. You can set the DAOS log file mask and the error level logging, and you'll be able to see a detailed log for each and every IO that is going to DAOS. And so this is from the compute node side, and you can also diagnose any DAOS IO from the server side as well, and you'll be able to collect the logs from each and every engine and the storage devices. You'll be able to see extensive logging. We usually place it in a common location every day, or you can send a ticket and we'll send you the logs from the server side as well. So the other one is with tools. Most of you would have been familiar with Darshan profiling, which helps you to profile POSIX, MPIO with all the nice heat maps and plots. Darshan does support DAOS. It has a very minimum lightweight overhead in profiling, and you can investigate and tune different IO behaviors and see the different patterns that happens. And you can also use the profiling at scale, so you'll be able to get the nice UI with HTML report with all the plots, even if you're using 8,000 nodes. It's not recommended. You can use with start something small and slowly increase the number of nodes. How to use Darshan with the first level of interface, the POSIX level. You just mount the POSIX container. The good thing with POSIX interfaces, there's no code changes required, and you can still use Darshan to instrument Darshan's POSIX module, and you'll be able to get the details in the report. I'll show an example of how the report looks like. And this is with the interception library. Same thing with POSIX, and you'll be able to collect Darshan statistics even from POSIX interception. And even if you're using the libDFS lower level DFS APIs, DFS init, DFS write, DFS read, you'll be able to instrument the full IO. So we usually have a module on Aurora, just to module load Darshan, and you should be able to get it. But in case if you want to build from scratch, build your Darshan profiler from scratch, you can follow this commands. And once you profile your IO or application with Darshan, you will get a dot Darshan file after your MPA exec. So that's the Darshan file that you collected. And now you want to create a report from the Darshan file. You can use the PyDarshan utility. Usually I take the .darshan file, bring it to my Mac, and get the HTML report out of it. This is a set of commands to install on your Mac. I think we do have the same PyDarshan module on Aurora too, so if you can also use this module to collect the report. So basically, after your MPA exec, you'll have the .darshan file, and then you load the module, set the LD preload, and after running this command, you'll be able to get the .html file. Or even you can get the text format as well for the monitoring and profiling. So in case if you have multiple libraries on top of DAOS, you have libp, netcdf, or HDFI. This ordering is important. So you first LD preload the darshan, then you preload the HDFI, then NetCDF, and then the DAOS interception library. So all this is captured to the higher level. This is just the ordering on the LD preload in your MPI exec. And if you're not using Python, and if you're using Fortran or C code, then all this goes into your GPU tile compact script file that Aurora provides. You just set all this environment variable inside the script file. Here I'm just showing some of the screenshots on how to profile your IO. And this is with a simple IOR that we saw this morning. These are the configurations that are used. It's just 2 nodes, 12 ranks, 12 GPUs per node, and the amount of data that it's writing to a POSIX location mounted on temp, pool name, container name, and this is the file where I'm doing the IO to. It's the configuration is single shared file and independent and so on. As I mentioned before, if you do not want the HTML report and you just want the darshan parser text level report, you can always use this binary and use the .darshan file that you got after MPI exec, pass it to the binary, and you'll be able to get the report, the profiling and monitoring. So once you have the HTML report from the PyDarshan module, you can load your HTML file into any browser, and you will be able to see all different plots showing the various IO happening for your code, and you can diagnose if it is not efficient and so on. So I'll just go over different plots that we get from Darshan profiling. So this is for the simple IO that's happening to 2 nodes. It just shows you how much time was spent on each level of interface. So it starts with the POSIX. So this is where you mounted it. So most of this is carried down to DFS, and it just shows how much time was spent on different interfaces. I think this stdio is because it is printing all this on the terminal, so there might be some time spent there. And we also have different heat maps that you can get from the profiling for POSIX, stdio, and DFS, and several other per module statistics on read, write, access, bytes written, and so on. And the operation counts for these are all from the same IOR example that I showed before. How many actual read calls that started from the POSIX gets carried all the way down to DFS. You can see 240 reads and writes goes down to 240 DFS, and these are all the print lines that comes in your terminal. And different access size. So how each of your IO is. So this is where you can link your DAOS chunk size and what's actually happening on the DAOS. If you set 1 megabyte chunk that goes from a compute node to a storage node, do you really see that 1 megabyte getting reflected in your IO and so on? And you can also monitor the consecutive access, sequential access patterns for POSIX, DFS. Yeah, that's it. So this is everything about monitoring. So we have seen the different ways to monitor DAOs from an interception level monitoring, client-side monitoring, server-side monitoring, using a profiler tool to monitor different access patterns to DAOs, and different ways that you can interact with DAOs and so on. Yeah, this is the end of my talk.
Okay, any question to Kasi? I have some questions. So you showed there is some POSIX API and the DAOS API in the application, right? So is there any, I mean, do you have any rough approximation to get how much performance you can gain through the DAOS API?
So you mean comparing this one using the DFS API from your code
Yep.
versus not using this and just pointing to let's say just using the mounted POSIX container, how much difference that you can get, right? So this is where the interception library comes in. So you would be able to get very close performance from POSIX level to DAOS level if you use this interception library. So just to give you a rough number, you would be able to get around 90 to 95% close to the hardware performance, even with POSIX, without using any of this DAOS APIs. You'll be able to get the maximum performance if you use the interception library.
Okay, I think that's great for users, but maybe less motivated to use this API directly,
Yes.
I guess. Okay.
Yeah. Definitely, you can create a different IO irregular access, or it's very similar to MPI reads and writes, right? There are very, all the APIs and arguments are even very close. So this would help us to explore new different IO access patterns. And there's also open source, so you can create new ways to access your data.
Okay. The another question is kind of could be a dumb question. So you showed the without redundancy performance and with the redundancy performance chart here, right? So I'm just curious, and on fly, we just use the no redundancy to get the maximum performance. And after finish the job, can we somehow change include some additional redundancy? I mean,
Yeah, that's a good question. Actually, if you are doing some simple experiments, you can do some quick tests without redundancy. By default, redundancy is enabled on Aurora, but this is not recommended because let's say if the DAOS goes down,
yeah,
exactly when your job was running, and you will not be, there's no data protection, right? You will not be able to build back your data. So you would lose your data if you don't use redundancy, but you get a high performance. So that's the cost for critical important results and checkpoint. You can use it. If it's not important, maybe for one checkpoint, you can set no redundancy. For every once in five, for others, you can set some redundancy.
Oh, yeah, that could be something we can try. Okay.
Thanks.
Any other question to Kaushik? So do you have something for the hands-on, or is it all you have?
Yeah, so for the next hands-on, you can try building on top of what we did this morning. You can change different chunk size. Maybe I can help with integrating your Insight applications to get the best performance, change configurations, try to get similar performance optimizations for applications. Can try different examples here.
Okay, so we can try.
Yeah, all right, thank you.
Okay, thank you.